Today for the Solve It session webinar. My name is Alice Ducois, and today we'll be talking about the challenges associated with understanding how abrasion affects mechanical systems. Here with me is Henry Smith, and David Blackwell will join us later for a Q&A session. So we'll be first explaining the abrasion mechanism, how it takes place, and what are the solutions available to maximize equipment lifetime. We will break this into sections, a 20-minute presentation and a 10-minute Q&A session. And this is where we'll address any questions raised during this webinar. So today we are going to talk about the biggest problem facing industry, such as pulp and paper, manufacturing, mining, which is fine particle abrasion. So abrasion is one of the most common forms of wear. It is ultimately a process, one which cannot be completely stopped. Everything will wear down with time, but there are methods to slow this process enough to allow equipment to maintain a good service life. But before we can talk about solution to a problem, we need to understand the problem. So abrasion is caused by foreign bodies moving over a surface. In most cases, these are mineral particles, and this particle can be harder or softer than the metal surface undergoing the abrasion wear. There are many forms of abrasion with many different names, such as gouging, grinding, or scratching. And these names mainly describe the cause of the abrasion and how the wear took place. So, for example, scratching abrasion could be due to small particles flowing through a pump. Grinding abrasion could be a process involving particles under compressive loads.
So if we know all this information about what abrasion is and how we define it, how we describe it, let me ask you guys a very, very quick question first. If I have two systems, one which transports crushed granite and the other one which transports crushed chalk, which of the two systems do you think is going to suffer the greatest amount of wear? If you put your answers into the comments, we'll go through them as we do the presentation. But it might seem like a relatively obvious answer in most cases. But presuming that both of these systems are made from carbon steel, do you reckon that's going to make it any easier to decide? Unfortunately, in this case, we don't actually really have enough information. So obviously any problems associated with wear, generally the hardness of the particles is probably only one piece of the puzzle. When in fact, the truth is that there are many factors that can affect how severe any instance of abrasion is. So as just mentioned in the previous slide, the type of material is only one factor. So we have our granite, we have our chalk, but you don't know anything else currently. The media, which is causing the abrasion, has a huge effect. So the size of the media, the hardness, the shape, all of this could cause this rate to vary massively. So a couple of examples of the factors you can see on screen at the moment. So the media type, is it a liquid, is it a solid, is it a gas? Generally a gas won't cause abrasion, whereas a liquid or a solid might. The media size, are we talking about, as Alice has said, the smaller, finer particles or something much, much bigger? Is there moisture involved? Generally, a wet surface will degrade much faster than a dry one. And also, what is the temperature in the system? So a higher temperature normally dictates a more aggressive type of environment. Once we've got all this information, we can begin to come up with some sort of a solution. However, the most important question, or what I think is the most important question of all, isn't actually on this list. In order to correctly specify a repair method for damaged equipment, ideally, we would want to know how long that equipment's been in service for. This gives us a really good indication as to the relative aggressiveness of the media involved. So if we have a pump that's been running for 30 years and has only just started to show some signs of wear, chances are that we can probably provide a repair solution for it. If we have a pump that's been running for 2 weeks and has already got a hole in the side of it, we're going to have to take a bit more of a cautious approach to repairing that substrate. So go back to my previous question, which asked which of the two, granite or chalk, would be more aggressive in our given process. And technically, the answer is both. Really, it depends. So the first thing that people consider when they're faced with a question like this, and as an engineer, I'm guilty of it as well, is that granite is a harder material, so therefore it should cause more damage. I don't think anybody's actually said granite in the comments, which is a good thing. So while that's true, granite is a harder material, we must remember all of the other factors. So we don't know anything really about this situation. So we don't know the size, we don't know the quantity, the velocity, or any of the other useful information about the process. Over time, chalk, as you've all stated, could quite easily cause as much damage. There might be one piece of granite going through this system every day, or there might be 25 tons worth of chalk going through the same system. So again, it depends on a lot of different factors as to how aggressive a certain media is going to be. And the more information we have, the easier it's going to be for a company who provides repair and protection materials to specify something that will work in the long term.
So where can we find abrasions? So pretty much everywhere. Every equipment in contact with foreign bodies will be subjected to abrasion. So solid handling equipment such as debarkers, hoppers, screw conveyors, conveyor belts, and drive roller are especially susceptible to abrasion and wear due to the nature of the material they process.
So if we're looking at the solutions that are available, you've seen how many different types of equipment there are, but you can generally break down abrasion into two types. So selection of the correct repair product is dependent on this type. So specifically the angle at which the wearing material is impacting the substrate. This can be defined as your angle of incidence. So the different mechanisms of abrasion are divided into either a brittle or a ductile type behavior, as you can see on the screen at the moment. The ductile abrasion deals with material removal due to like a cutting or a ploughing, sliding abrasion, where the angle of impact is typically less than about 30 degrees or so, with respect to the target surface. On the other hand, the brittle erosion is material removal due to more of an impact type force. So we're talking like 90 degrees or up to 90 degrees, almost perpendicular to the affected surface. And this effectively causes cracks, and it's a brittle fracture in the material, which causes loose material on the surface to then come away from that same surface. So if we want to select the right material for this type of application, this is always influenced by this angle of incidence. So angles under the 30-degree limit, the threshold, the harder materials usually perform much better. So epoxy coatings, whereas the elastomeric materials tend to cut and tear more readily. So they get increased wear rates, whereas the epoxy materials get lower wear rates. At a much higher angle of incidence, so up to 90 degrees, the harder materials tend to experience the elevated wear rates, resulting from increased fragmentation and spalling. So you imagine you have something really hard hitting against the surface at a right angle. The elastomer materials are more effective in this sort of condition, mainly because the impact energy is sort of absorbed and dissipated via elastic deformation rather than a plastic type deformation. And then finally, we have instances where you have what we call erosion corrosion. This is where you'd have the dual impact of some sort of mechanical abrasion or erosion and the corrosion process in there as well. Now, this dual acting process acts a bit like a vicious cycle. So that top layer of your steel gets corroded, much weaker. Abrasion comes along, removes that corroded material. Fresh layer then corrodes, that then abrades, and it's, as I said, a vicious cycle, constantly repeating. So that's where you get the largest amount of wear rates. This would also be where we use a combination of both epoxies and elastomers to combat the issue, to prevent the corrosion and slow down the abrasion and the erosion as well.
So when dealing with sliding abrasion, a hard coating is often prescribed. And we have a range of hard-wearing lining options, which have been optimized for both dry and immersed abrasive service. So for dry abrasion, there is Belzona 1811, so used for large particles, such as those found in the mining and quarrying industry. Belzona 1812 is a modification of Belzona 1811, and this gives protection against much more thinner particle. So a good example of this would be in pumping equipment involving water and small solids. Belzona 1813 is designed for dry abrasive service up to a maximum temperature of 200 degrees. And finally, Belzona 9811 can be used in conjunction with this other product in order to give maximum abrasion resistance reserved for the harshest of operating environments. So now we are going to show you a video, and in this video we demonstrate how to apply an abrasion resistance system with Belzona.
Okay, so we've just seen a video that shows some of our products that we use in the case of ductile abrasion. So for the case of brittle type abrasion, because of the higher impact angles, remember up to that 90 degrees, the elastomeric type products are frequently specified. So these harder elastomer rubber, effectively type materials, tend to absorb the impact forces and then deflect the impacting materials. So the ones we normally start with for a high abrasion service, we go for the hardest elastomers that we have, which is the 2100 series, which they're designed specifically for really heavy abrasion service. So things where a normal rubber lining or something like that may not stand up to the wear. For the high flexibility, we have the Belzona 2200 series elastomers, which are very, very similar to the 2100s, but due to reduced hardness, it also means they're more flexible. So in areas where you require service from a product that has extreme expansion and contraction, or you require really high flexibility, these would be the products that you go for. And then we finally have, for emergency repairs, the Belzona 2300 series. So it's just Belzona 2311 in this series. It's fast curing, polyurethane, again, much the same as the others. It's for high speed emergency repairs. So a common example for this is torn conveyor belts in the mining and quarrying industry. Which will show you shortly some of the abrasion resistance of the 2121 product on a test video later on in the presentation.
So we also wanted to show you some case study from around the world. So you can see how Belzona can be used in practical and real life scenarios. So Belzona has a fantastic library of case study, all available to the public at khia.belzona.com. So as a first example, in this application, the screw conveyor at a water treatment plant in Romania was suffering from significant metal loss. And as a part of its operation in a treatment plant slurry clarifier, the screw conveyor was transporting dehydrated slurries, and the hard particles in the slurry were causing abrasion of the conveyor blades, as you can see on this picture. Due to the particles being incredibly small, Belzona 1812 was specified as it can deal with thinner materials. And the blades were prepared and coated in accordance with the instructions, and this allowed the conveyor to continue operating in such a harsh environment, with minimal wear to the base materials of the blades.
Yeah. So a similar sort of example, but this time it's for a mixer blade inside a crystallization tank. So rather than the ductile type abrasion we saw in the previous one, this is more of the brittle type. So this is, as I've already said, part of a tank system, which is in an FGD system, so flue gas desulfurization. This effectively, it removes the sulfur from the gas. It's part of that system, and it's quite a common component in power plants all around the world. Now, they found when they took this tank out of service that the mixer blade, as you can see in the picture on the left of the screen, is pretty much gone. It's not going to be doing much mixing, and it's the remaining of its lifetime. What they did was, rather than remove it, buy a new mixer blade and then reinstall it, they just wanted to fix it while it was in service, in place. So they used Belzona 2111, which is the DNA high build elastomer. It's like a paste grade type material. That rebuilt the blade back to its original dimensions. And then they used Belzona 2131, which is a fluid type, similar sort of properties, but it's a different consistency, different viscosity. And they used that, as you can see on the right-hand side picture, to repair and protect the blades from further damage, also protecting the rebuild material underneath that as well. And they actually found the financial saving they gained from doing the repair rather than the replacement route meant that it can also fix another mixer blade in a different tank within the same shutdown, where normally they would have had to have waited for the following shutdown the next year to then fix this other tank. So cost savings all around for the customer. And again, going down the more severe route, so this was kind of a dual action. This was brittle erosion and ductile erosion abrasion as well. This was manufactured in Canada. They made asphalt shingles. And basically these hoppers they take the asphalt shingles, which are probably less than a millimeter in diameter, so really, really tiny particles. And they found that the hoppers just couldn't cope with the service. So what they did was they used Belzona 1812, the ceramic carbide fine particle version, to combat the ductile, the sliding abrasion they got from dropping these shingles into the hopper. And then you use the Belzona 2111, the same as in the previous example, to cope with the initial impact of them hitting the side of the hopper and then sliding down the outside. So to give you a bit of context, this hopper actually deals with about 22.5 tons of material every single hour of every single day. So it's a lot of material going through it. And in a year, they only have the 40 days of every year to do the shutdown and perform maintenance. Originally, these hoppers only lasted a month, so there's no way they get between the two shutdowns. They found other solutions, got them to 7 months, and then with the Belzona solution, this is actually increased now to 18 to 24 months, so 2 years of lifetime with no maintenance whatsoever. And now they can even carry 1 or 2 hoppers in stock ready. So if there is an issue, they can remove one, replace it, and it's already repaired. It's already protected with the Belzona products. So they can carry on using this material for further refurbishment work in the future. Now, all of these materials have their own individual merits, as was explained. So as Alice said about the 1812, it's for fine particles. The 2000 series have their elastic properties that makes them good for brittle type abrasion. However, a lot of these products do also have shared features as well. So things like a lot of the products are 2 parts. They've got easy to follow mixing ratios, easy instructions. They've got good general mechanical strength, chemical resistance. They're applied with very, very basic hand tools and so on. The list is quite long. And all of these products are also tested in order for us to give customers, give clients an indication of how well our products will work effectively in terms of their abrasion resistance. So the testing we do on the products, we have numerous test methods. The stuff we do in-house is our ASTM standard testing. So Tabor abrasion testing and the slurry abrasion testing. So these are things you guys might have seen before. But we've also completed some third-party stuff. So the impact grip blast and the slurry jet impingement towards the right of the screen at the moment. These were things we did where we sent our products out to a third party to verify and give us the most realistic example of how our products would cope in an abrasive situation. And all the results for these can be found on our individual product specification sheets. So if you wanted to know how well 2111 performs in an abrasive service, go onto the specification sheet and it will give you a value which we receive from these tests, which is generally a good way to indicate how well any product will perform in any type of abrasive service. So now we're going to show you another quick video on how we do some of this testing for some of our abrasion resistant materials.
So maybe you've sat listening to this webinar right now, wondering how this application can actually happen. If you are curious, we do have the Belzona YouTube channel. This contains video of everything from product-specific examples to instructional videos for specific repair. So we are also beginning to introduce the Belzona in action, which links to our case studies and gives a much more detailed view of the job we undertake with our product. A large number of this video are actually also available in other languages. So if you are located much further away, you can still benefit from our advice and guidance. So we hope we're giving you a good overview of some of Belzona 100% solid epoxies and how they can be used to effectively repair and protect against abrasion and wear. So if you want to find out more information after a Q&A session, you can check out the website. There you will find links to your local Belzona distributors. And as you can see on the map, we are represented all around the world, and regardless whether there is a little flag on your country, there will always be someone dedicated to help your region with more materials. So thank you for watching this webinar today. We are now going to have a Q&A session with Henry, and we are welcoming David Blackwell. So if you have any questions, please type them into the chat and we'll answer them as we go through. So, hi, David.
Good afternoon. Good afternoon. There we go.
So I don't think
Good afternoon, everybody.
So I don't think I have any question at the moment.
No questions? Let's have a look. Must have done a very good job, Henry. No questions.
That's the problem.
No questions yet.
Morning, Burkhard. Having a bit of sunshine over in California.
Bert.
Yes.
Hey, Burkhard, how you doing? Oh, I think there's a question coming in.
Sean.
So Sean is asking, how quickly can your elastomer materials be returned to service?
Basically, that depends on the ambient temperature. Because they're 100% solids, they contain no volatile solvent. You can actually force cure them as well. It's always a good idea to allow them to set to a dimensionally stable condition, which would take, depending on the material, but on average, let's say 20 to 40 minutes to set dimensionally stable. And then you could introduce external heat, hot air, something like that, to increase the ambient temperature, and that will force cure the material and allow them to go back into service much quicker. Generally speaking, for every 10-degree rise in temperature over ambient temperature, you will halve the cure time. That's just a general rule. It varies slightly from product to product, but that's a general rule you could use. Okay, hope that answers your question. Next question.
So we have John Paul from Berlin who is asking, we have a screw conveyor handling ash and bark. We use hard face welding. Would Belzona be a good alternative?
Yeah, it's a difficult question, that. We do quite a lot of screw augers, and we're very good, our materials are extremely good at protecting the shaft and the face of the screw threads themselves. On the edges of the vanes, you generally find hard face welding. And the problem there is, if you've got hard face welding on there, number one, it's extremely difficult to get the surface profile, the minimum 75 microns that we require to get good adhesion. And number two, any relatively thinly applied epoxy coating applied in that area, right on the edge, will not perform as well as hard face welding. And that's because, dependent on the clearance between the edge of the vane and the container on inside which the vane is running, there will be friction, and that friction will generate heat. As the edge of the blade gets hotter, of course, the material becomes softer. So generally speaking, on the edges of the vanes, stay with hard face welding. It's about the best option. But on the flanks of the vanes and the shaft itself, then Belzona can give you extremely good service.
So we have a question from Teja. Can we apply 1812 on slurry pump?
Yes, you can apply 1812 on the slurry pumps. Again, it's kind of a general statement. Theoretically, the answer is yes, but you need to take into account the substrate of the pump. Generally speaking, for slurry pumps, the substrate is not your run-of-the-mill cast iron or steel. It's generally some kind of hardened chromium steel, chromium nickel steel, something like that, which is extremely hard. So it might be difficult in the first instance to actually grit blast the pump to get the minimum required profile. So provided you can get the profile, then yes, you could use our materials. Again, dependent on temperature. As the temperature, the ambient temperature, or the operational temperature increases, you get closer and closer to the heat distortion temperature of the material. That is the temperature at which the material begins to become more plastic, and therefore its physical properties begin to fall. So provided you stay well under, within about 10 degrees below the HDT of the product, then it should perform very well. Is that it?
So do we have any more questions?
Any more questions? If I haven't answered the question as fully as you would want me to, please come back and I can expand. But obviously, time is a limitation, so I try and get most of the answer in quickly.
We have another question from John Paul. What are your typical cure times?
Typical cure times?
Depends on the product.
Well, it depends on the product and it depends on the temperature. But all of the data sheets will give you a chart that tells you what the cure times are dependent on the ambient temperature. As I said, with most of the Belzona materials, because they're 100% solids, that full cure time can be reduced by the application of external heat source, provided that the materials are allowed to become dimensionally stable beforehand.
How fast could we expect to put the equipment into service after repel protection?
So there's the bit on the instruction sheet for each product. There is a section specifically saying, in this case, you'd be looking for the full mechanical service or hardness, and that's a specific point on the table that Dave was already talking about. So if you knew it's going to like a dry abrasive service, there's no chemicals or anything involved, you could wait until that section, it's had that cure time, and then put that back into service. It depends entirely on what type of service it's going into, which is why we stress so much about having all of this information listed out for us every time we answer one of these questions.
If you're looking for a generalization, for full immersion and chemical resistance, most of our products will need at least 7 days cure at 20 degrees C. If you cure them at 40 degrees C, that will drop to somewhere around 3.5 days. If you cure them at 50 degrees C, it will drop down to maybe 1.5 to 2 days. If you cure them at 60 degrees C, it can drop down to 24 hours, and it carries on like so. You can cure our materials once they become dimensionally stable. You can heat them up to at least 100 degrees C without doing any permanent damage to the material. So by force curing at 100 degrees C, you can drastically reduce that full cure time. Obviously, you wouldn't put them back into service until the material has cured and has cooled down back to ambient temperature.
So can we find this information online on the website, or would you be able to send me something after the webinar?
Everything is on the website. So if you go to the Belzona website, all of the data sheets for the various products are available there in various languages as well.
And we can send you something after the webinar.
But we can also send you it from the webinar. If you email us with the address, we can, or your email address, we can email it back to you.
Yeah, there's also the Belzona app as well now, which includes all the data sheets as well. So you don't even have to be on a computer. You can just have it on your phone as a reference guide if necessary as well.
Yeah, if you go to the App Store, you can download the Belzona app free of charge. And that will also, as Henry implied there, give you all of the data sheets for all of our products on your phone, at your fingertips.
And in German also.
Yes, yes. The main ones, yes, they are translated into German as well.
Yeah. Is that John Paul?
Yes.
Yeah.
Okay, so if we don't have any other question, we're going to end this webinar now. So thank you so much for coming and for attending this webinar, and we'll see you soon for the next one.